red giant stars. So please take it away.
Okay, thank you. I'm gonna share my screen. Can you see it?
Looks great.
Okay, thank you. So I'm gonna talk about some results from my PhD project. Actually, I'm finishing my PhD next week, so it's part of my thesis. It has been published already, the part I'm going to talk. It has been done with the collaboration of these amazing people. So basically, it's a work on galactic ecology. So after the revolution that has been yielded by Kepler and Gaia in galactic astronomy, we could probe further in both in our understanding of the galaxy and of red giant stars themselves. So some recent studies, they have shown that some of these red giants are displaying conflicting characteristics when compared ages and metallicities. Like we expect that younger stars will be more metal rich, but some of them have been noticed as metal poor, which is kind of conflicting. So our goal in this work is to combine both gas astrometry, study their kinematics, using seismology from Kepler to determine their fundamental parameters with great precision, and using spectroscopy from HIRIS. So we are going to combine these three methods to do an exploratory analysis of these weird stars and see what kind of information they are hiding for us. So just a quick detour for those not familiar with seismology. We are talking about solar-like oscillations. So we are studying cool red giants, FGK red giants that display solar-like oscillations, like the same type of oscillations as the sun. They are of very low amplitude, so we need Kepler to study these solar-like oscillations and how we use the information from these oscillations. So there are two main parameters. One is delta nu, which is the separation of the frequencies of the same angular degree, and the other is the max, which is the center of the excess in the power spectrum when we convert the light curve from Kepler to the Fourier space. And we have some scaling relations. It has been shown that these quantities are related to effective temperature and mass and radius, and hence also surface gravity. And we can scale these relations to the sun and then calculate masses and radius in solar units. But the first works that have been studying stars in the halo in the Kepler field have been shown that there might be inaccuracies in these scaling relations. They work very well for dwarfs, but not exactly well for giants, probably because of the fact that the internal structure of red giants is different from the sun, so they are not homologous, and we are scaling against the sun, for instance. And also, some later studies with eclipsing binaries have shown that those astrosysmic relations shown in the previous slide, they overestimate the masses. So since then, several studies have been trying to calculate corrections, second order corrections. So here we see the study from Epstein et al. 2014, showing that the masses of some halo stars that they studied in the Kepler field, the masses are higher than the region of the value of the masses that they were expecting for halo stars, which is in the gray area. So our goal is like to get data from Kepler from all the years of observations and combine with spectra that our group has observed in HIRIS, high resolution spectra, to do detailed chemical analysis and do grid-based modeling to calculate masses and ages in particular with the greatest precision possible. So we selected in our samples some of the stars that they should be, according to their metallicity, they should be less massive than they actually are. In this diagram, the horizontal axis shows that a quantity that is proportional to mass, at least to first order. And if we take the color scale into account, these stars should be more to the left in the diagram. So basically, we are analyzing some metals poor stars from the halo. So from the abundances, we did a comparison with the stars that are in common in our sample and apogee, just to check if our metallicity scale is correct, and for most elements is fine. There is this point here in calcium, for instance, but is actually a bad measurement in apogee. So from our results here, we are comparing like each ladder represents one of the stars in our sample that are in common with Epstein 2014. And the most important points here are the cyan and blue. So the cyan is a reanalysis using our method, but the observables that were published by Epstein. So we used their effective temperatures, we used their values for delta nu and nu max, and etc. And here we can see that the ages that we calculate using their observables have very large error bars, while the ages that we calculate using like infrared flux method temperatures and using metallicities from our spectra and log G's from seismology and so on. Here you can see that our error bars are smaller, but our masses compared to the gray area, which is the range of mass expected for halo stars, for most stars, the masses are still too high, at least compared to what is expected for halo stars. So we did apply the corrections that have been calculated in the previous years, but still the stars are too massive for the expectations for old halo stars. Just reminding that in red giants, masses are a good proxy for age. So at least one of the stars, a star B, apparently it might be an evolved blue straggler. So we suppose that this star, which is one solar mass and the age is 5.5 giga years, which is a very metal poor star, high alpha, low metallicity, as confirmed from our analysis with high resolution spectrum. So it's too massive, too young, and too metal poor. So from the Gaia astrometry, we noticed that the real value is 2.8, which is considered too high. It's expected to be around 1, at most 1.4. And there are recent works in the literature showing that our high rho might be related to binaries. So this star might be part of a binary system, and it might have accreted mass from a companion some time ago. That might be one explanation. So we also, since these stars are in the halo, we also study their kinematics and try to compare to several of identified accretion events identified recently thanks to Gaia. And here, for instance, we have the action space, we have inclination against eccentricity, orbital energy against angular momentum, and so on. And we're trying to check from which of these events, like Sequoia, Sausage, or Temnos, are the most similar ones to our stars. From which of these events they match kinematically, but not only kinematically, chemically. So we did a comparison with a recent work that has identified some stars of these accretion events and has measured their chemical abundances also with high resolution spectra. And they have fitted like an alpha Ni for each of those events, and we did try to compare the chemistry. So, but this is a large phase space, so it's better to summarize in one big table. So here we are comparing each star of our sample with several dynamical and chemical parameters. And basically the green columns are stars that are likely to have been accreted, but we can say they have been. At the other columns, we don't have enough information. So as a final result, an unexpected result was like that when you use parallaxes to model the ages become very sensitive to variations of parallax. So the 0 point of the parallaxes must be very well calibrated, which is the case in Gaia DR2, but apparently not in the early results of Gaia DR3. So just wrapping up, this was an exploratory study combining 3 different methods to gather all the information we could from these stars. The masses keep being higher than expected, at least for the sample from Epstein 2014. Assuming that these objects are from accretion events, we could use them to date a lower limit for the age of the accretion event. And also it can be a method to identify evolved boost travelers. So that's what I had to say. Thanks for your time. I'm open to questions.
Okay, thank you, Arthur. Do we have any questions from the local audience at Caltech? We don't yet have any on the Slack channel.
Joshua, I do not see any hands in the room currently.
Okay, then perhaps I'll ask a question. So on the slide when you were speaking about accreting groups, can you give a little bit more detail about what that means? What are the groups that have been potentially accreted?
You mean this slide with the table or this one?
That one is fine. Yeah, what are these groups, Tamnos, Sequoia, and Sausage?
So basically, with Gaia DR2, people started to identify, several works started to identify in the halo accretion events that are probably related to mergers. And in the case Sausage apparently is a kind of major merger with the Milky Way. So these stars probably have been captured from dwarf galaxies which have different histories of star formation, and then, for instance, different profiles in the alpha against iron diagram. So from this information, we might suggest, but not say that the most, at least some stars in our sample might have been accreted in these mergers. And that would explain why they are more massive and hence younger than expected for the Milky Way halo, because they were formed in environments that have a different story.
Okay, thank you. Okay, do we have any questions in the room?
No, no hands in the room, Joshua.
Okay. So I guess we'll have a final call for questions. Don't have any online yet.
Yep, I think that's it.
Okay, well, thank you very much, Arthur,
Thank
for the
you.
nice presentation. And also thanks to all the speakers in this session and to the audience for their nice questions.